All right, so now at this point we are ready to bring our understanding. Well, we built our understanding and we built our foundation from the financial math, but now we are ready to step outside of the world of the financial math problems, but still carry over our understanding from what we have built when we were doing the financial math problems here, and you will understand exactly what I meant just now as soon as we get into doing some of the actual problems. So just a quick recap here, but when we were doing financial math problem, we've learned about the concept this. So it's a growth. It's clearly speaking, when we were doing financial math, then money was growing according to our investment right there, and money was growing exponentially. But what I really tried to emphasize was there was a difference between a nominal rate, okay, and then there's an effective rate right there. And the effective rate is measured in terms of the periodic the effective rate is indeed understood as the observed periodic of the growth rate right there, like and of course based on our default time period, okay. And so now with that understanding, now we're gonna take all of that understanding about there's some quantity is growing with a growth rate right there. Okay, but then we're going to take that understanding outside of the financial math problems, outside of the world of financial math problems, where we're now going to be looking at population growth, bacteria growth, or the decay process of of an element. Okay, so those are all the different all of the other natural phenomena where the growth or the decay follows an exponential rule, as I have stated earlier, even before we got into the financial math problems. But then we're gonna start carrying over all of the concept about the nominal rate and the nominal rate and the effective rate. We're gonna carry those concepts, or at least the understanding about those concepts into those problems other than the financial math problems. Okay, but yes, be aware that we will, as we step outside of the world of financial math problems, then we will no longer use precisely the term nominal rate or effective rate. Okay, but we're gonna be using some other term. But each term there will be some analogous meaning. So a nominal rate will have analogous will be analogous to some rates that when we deal with the natural growing or decaying problem right there, or the effective rate will have some analogous term in the world of the natural growing or decaying problems. Okay, and so to really make it clear about what I was just now saying, let me just bring back quickly that problem 3 I introduced earlier, where it was a problem about the financial. All right, so let's one more time look back at problem 3 right here. So problem 3 started out giving us simply $4,000 being the initial amount. And so now clearly at this point of our learning, then clearly this problem right here is indicating that money is a quantity that's growing. Okay, and we have a rate right here. So interest rate, basically growth rate in the concept of financial math, in the financial math concept, and we refer to that as interest rate. And I have spent a good amount of time explaining all of that in details in the earlier part already. So now this rate here, we got rate, we have initial, the amount right here. So what we've been through is that, yes, we have, let's say Q here is the quantity or the amount in T years, okay? And then from that way right here, then we can have, so I only need to recap what we've done so that we can have a good comparison, and then we're going to take that concept and move on to those problems as I promised, outside of the financial math problems. So again, quantity here, Q of T, is some amount as a function in terms of time right here. So that Q of T is the amount in T years. And so we have Q sub 0, which is the initial amount being 4,000, okay? And we have that rate right here, and simply right out of the box, that rate was just simply indicated. It's increased. The amount is or the amount increases by 7% per year. Okay, and sometimes we refer to that as 7% annually. So we have that rate, and so that's why these are the equations that we have seen. These are the equations we have seen right here. So the most natural one was when the interest was compounded annually. Okay, when the interest is compounded annually, then Q of t was found as an exponential function, being 4,000, being a coefficient, times 1 plus 0.07, okay, and then raised to the t. And then I've spent a lot of time explaining, and in the end we drew out a conclusion that this rate right here, and that's how it is. A lot of times, a big percentage of time right there, a large percentage of time right there, this rate right here in financial math, in the world of financial math, this rate is, in a good amount of times, is given as a nominal, rate. Okay, and I just want to highlight that term again, even though I already gave that clear explanation of what nominal rate is all about. And so a big amount of times when a problem is simply just given out to you, a very high chance that it's intended to be the nominal rate. And then when we simply just compounding the interest, when we're just compounding the interest based on whatever the default time period right here. So the default time period here in this problem is per year. That's why compounded the yearly is gonna make it precisely just that nominal interest rate. And so APY equals APR. Okay, so this is exactly the nominal rate as well. Okay, and we have two versions. I mean, this is one version where that nominal rate comes exactly and becomes the base of becomes part of the base of our exponential function. And so the final form is going to be 4,000 times 1.07 to the t. So that's the final form. But so we were using the nominal rate because here the compounding frequency is the same as the default time period. The compounding frequency is once per default time period. Okay, and so I really emphasize that concept quite often throughout the earlier part of this lecture. And then we went on to the concept where we keep increasing the compounding periods, the number of compounding periods per default time period, or basically we keep increasing the frequency of compounding per default time period to the point where we have what's so-called, to the point where we refer to as we compounded our interest, or our interest is compounded continuously. Okay, and this is where I mentioned somewhere here and there in the earlier part, our money was growing continuously. Our money was growing continuously because interest is calculated continuously and then keep accumulating on the previous amount like that. And so now when we're compounding our interest continuously, then the function, the quantity becomes an exponential function still. And allow me to skip all of that explanation where it came from, because at this point anyone already knew. I'm just recapping. So now it's 4,000, the initial amount, and then it comes out to base e, okay, to the raised to the power of 0.07 t. All right, so this is another exponential function, but strictly in base e, because our quantity is growing continuously. Our quantity is growing continuously. But see, we start out with something growing discretely, making a jump. And I also emphasize on the fact that when it was money, when it's financial math, it is entirely possible, at least in a human world, because we can control this. The bank can control to offer you whichever compounding the plan that is. That's the idea right there. That's why this kind of problem exist in completely possible. Okay, it is entirely possible for a plan like this to exist, where simply just a nominal rate given, and then the bank is going to just calculating your interest just once a year, or once per default time period. Yeah. Okay, because this is the kind of problem where it's made by the human, so the human has control over it, and then we can decide to make it grow continuously or not. It's money. It's our property right there. Okay, and so now, but again, as a major highlight here, when it becomes something that grows continuously, when this quantity is considered as growing continuously, then we have to start using base E. Okay, but then as we switch over to using base E, then yes, there will be some difference in the amount of yield right there. So growing our money continuously will definitely make it more grow. We'll make the growth bigger. We'll make the amount of growth larger than the compounding once per the default period of time. And that's why we came up with the equivalent formula that. So from this one right here, we came up with the idea about there's an APY. Okay, so with this problem right here, there's an effective rate. Okay, there's an APY is now at this point in our understanding is the same as an effective rate. So RE, effective rate, is the same as is related with. So this is nominal rates, but effective rate is related with nominal rates through, the equation. Effective rates plus 1 equals e to the k, where this k right here is our nominal rate, and that's why in this problem right here we can easily recalculate. So how about, I'm running short of space, so let me quickly swing over to the other board and do a quick calculation, and I'll come right back here. And so now that we know our e to the k is e to the 0.07, right, in that particular problem 3 right there. But this is the nominal rate. And so back to what I was in the middle of saying, effective rate is always related to nominal rate in this equation. 1 plus effective rate equals e to the k, where k is the nominal rate, effective rate. Because effective rate now is sort of like put things in the periodic growth rate right there, where this is continuous growth rate, kind of like that. But thus trying to force continuity into something going periodically. Okay, so, or another way of how I explain that, this is observed. This is observed. Okay, I tend to use the term observed periodic rate. Okay, and periodic, I mean, whatever the by default, whatever the default time period that is. It could be per year, it could be per month, it could be per day. Okay, but so once we know our periodic, our default time periods, then this effective rate right here is basically whatever the rates that we observed once we know our money is growing continuously. Okay, and so now, but back to the formula. For this particular problem that I was in the middle of, then so RE, effective rate, is e to the 0.07 minus 1, because we can just subtract 1 from both sides of that, from this relationship. And then that is the reason why now quickly on my calculator, I came to approximately 0.072508. Okay, so it's close enough to 0.07. So this was the nominal rate. Like again, the rate before the continuous the continuous compounding process kicked in right here. But now once we allow the money to grow continuously, then really, we observe that in each default time period, the money has grown by that rate right here, which is slightly bigger, slightly higher than the the nominal rate that was given initially. Okay, so here, precisely speaking, it's 0.072508 right here. So even if I go with with only 5 decimals, then the effective rate as a percentage is about 0.072508. Okay, even if I round, and the real calculation went a lot longer, but I already rounded down to 6 decimal places. Okay, and then in percentage, it's 7.2508%, which is, I mean, in the world of making money, this makes some higher percentage than 7%. This is already 7.25, at least 7.25%, where this is only exactly 7%. Okay, so there's we saw a noticeable difference between effective rates and nominal rates. Okay, so now this is the rate where back in our problem, we are still talking about continuously compounding our interest, but alternatively, so it's not this form any longer, but alternatively we can, and I also explained all of that in details already. So alternatively, the same quantity that's growing continuously, but we can express that in a different with a different function. So Q of t here can also be written as 4,000, okay, times 1 plus point, see, and now we use our effective rate, 0.0725, okay, 2508, and then to the t. So this is the version where, so these two functions are exactly equal to each other. Okay, these two functions, they just, the different ways of expressing it. And this form right here is expressing the quantity as a growth in terms of the growth rate, in terms of the periodic growth rate. Whereas this is we now refer to that as continuous growth right here. Okay, but now this form right here is in terms of the periodic growth again, but the rate here is a nominal rate. Okay, so now we realize that for financial math problems, there's 3 different forms of the function, how we can model the growth. So one form is we write the function as a growth, where the growth factor here is based on the nominal rate, whereas here is the effective rate, or we use the nominal rates, but we use base E. So 3 different forms. Base E raised to the power of kt, where k is the nominal rate, or when it's continuous, base 1 plus effective rates, and raised to the t right here. Okay, so but here we no longer have to use base E, and then the effective rate has this relationship with the base E right there, or with the nominal rate. And so in that way, we know that for financial math, we always have 3 different equations like that to work with. Okay, and because this kind of a function, this kind of the modeling function right here, this style of modeling function staying with nominal rate is still existing in our financial math problem, because we're not only compounding continuously outside of compounding once per default period of time. Okay, but we can also have compounding monthly, which is 12 times in one default period, or we can compound quarterly, that means 4 times in one compounding period. And that's why for only in financial math we still stick with the starting one here. I see this, I tend to see over my years of working with this stuff, I tend to see this as the starting one, where we use the nominal rate. Okay, so nominal rate is like the starting one, and then we build the other rates. We build effective rates, and we build base E out of that nominal rate right there. Okay, so that's everything we picked up and we finalized about the financial math problems. And so now, just like what I was just said earlier, right before we got into this part of the lesson, we're now ready to take our understanding here and step outside of the financial math problems. We're going to start looking at those other problems outside of financial math. Okay? So now one thing before we start our journey there to walk outside, to step outside of financial math, one thing I can clarify for you, one thing I can be clear with you and yelling out loud now. When we're now working with those natural growth or decay of a population, no longer money, okay? This money stops right here. But now when we're stepping outside of financial math and we're working with population growth, I mean, I'm talking about human population, I'm talking about animal populations, I'm talking about bacteria population, I'm talking about chemical decaying, okay? Those are natural processes where it's either growing exponentially or decaying exponentially. Any of those processes outside of the financial math problems here, any of those processes is always, and at least if it's not mentioned, then we can always assume, okay? At least if it's not mentioned, then we can always assume that any of those processes, any of those natural growing or decaying processes is assumed to be a continuous growth or decay. That's the one thing you need to get clear with me before we can move on. Okay? So any other natural growing or natural decaying process is automatically a continuous model. Okay? A continuous model, or you can think analogously as, if those were money, then we are, we already see them. We already see the world here, those natural processes as something that's after the effect of compounding interest continuously. That's the idea. Okay, so really nail that down for me right there. All right, and so if that was the case, now once we step outside of the financial math, and if that's the case where any natural process out there, either the exponential growth or the exponential decay, any of those natural process is already considered as a continuous model, then we really don't have this form of the function, of the modeling function anymore. We don't really have the form like this where, initial amount times 1 plus the nominal rate. Okay, the nominal rate concept still exists, but we don't use that directly in our base. In other words, this form right here, compounded once per the period of time, doesn't really exist in the world of natural growth or natural decay processes. Okay, so now allow me to write down that quick line that I said right there. Okay. Any natural process, okay, either an exponential growth or a decay. That's what I mean by a natural process. So any of those natural process, aside from the financial math problem, aside from money growing, okay? Sadly, I have to say this, but aside from money growing, okay? So any natural process aside from money growth right there must be a continuous process. And even if it's not stated, a lot of times indeed it's not mentioned in a problem, but we just have to understand behind the scene that the process there has already been a continuous process. Okay, why is that? The number one thing, we are the human. We really cannot control the nature. Okay, So for example, now let me quickly bring back one problem that we looked through earlier, but we only looked at some problem to introduce us to the exponential, to the application of exponential functions, but there are still a lot more to look in depth of these problems. So, all right, so how about right here, right in our problem 1 right here. The population of Utopia was 25 million in year 2000 and has been growing by 4.5% each year. And this is where I need to make it clear like this. See, throughout the entire wording description of this problem, nowhere it's indicated that the growing here is a continuous growth process. Nowhere in the wording of this problem indicated that it's a continuous growth process. But now we just have to think about it and see how it makes sense that it must always be a continuous growth process. Because think about it, even if the wording is making it seem like, yes, the population grows by 4.5% each year. It's deceivingly makes it seems like it grows like that, but in the end, it's every day, every instance, there's new human being born in that nation. Okay, or having new babies being born is only one thing that explains for the population growth. Every instance, every new day, every new second, there's new citizens coming in. That's why we have a population growth. Okay? And so what I'm trying to say really is that starting out in 2000, we knew that there were 25 million, but it's not really happening like the whole population stays the same throughout the whole year until, 2001, and it's raised by magically another 4.5% of the population. It's not going to happen that way. Whereas in money, it does. Because like I said, we can control how the money grow is under our control. We set up programs, we set up machines so that once we set out that rule right there, then in the next year, then yes, we can wait all the time until next year, exactly a year, exactly one default period of time away, and then the interest calculation kicks in. But now population growth is a natural phenomena. That population growth problem right there, we cannot control. We cannot force the people to grow or not grow. We cannot force the number of people to grow or not grow. That's the idea. So it's not going to wait. So the population is not going to wait for another exact 1 year from 2000. So it's not going to wait until 2001 to boom, have another additional 4.5% of the population added to it. It's not going to do that. But as a matter of fact, it's a steady continuous process from every second and instance after 2001, after whatever the time instant that we measure, that we observed, there were 25 million. And then ever since that instance, every other instance after that until exactly 1 year later, we observed that. So exactly 1 year later, all we can do is we observe that it has grown by about 4.5%. Now I'm using that term observe. See, so now for us here, now if once we step outside of the world of financial math and become scientists, we have to give up the idea about being able to control the things right here. We won't control. The only thing we can do is we observe and we experiment. That's all. When we're studying about the nature, we only observe, and whatever there is what we're recording, what we have observed and recorded. That's the idea. And so now I start bringing out that term. We have observed. And so now if we're looking more closely right here, all right. I'm still leaving that there. So now I know that the process for population growing must be a continuous process. Okay? But then that rate right there, that rate's 4.5. So when I went through that problem a little bit already. Okay? I went through that problem to show how we can derive the function a little bit. But I did not formally say that was the function, and I did not have a chance earlier to really go in depth, because at that time earlier in the lecture, everybody was just at the very beginning. Okay, so I was only introducing the idea to enforce that exponential function exists, but I did not formally come to a final conclusion that function like that is the function, or what kind of function that is. Okay, so now we clear that the process there for that population growth has to be a continuous process. And so now what? Yes, if we're reading the description carefully, so the rate there, and it's not even written clearly. It's just it's only stating that rate is, it's growing by 4.5% each year. So it's a rate per year, okay, 4.5% per year. So right from this information, all we can extract is that this is the default. All we can understand is that this is the default. Per year here is the default time period. So one default time period is 1 year. And so that means that our time here, our t here is measured as time in years. Okay? In some other natural processes, it only takes days. It only takes hours in some other natural processes. Okay? And so now, back to what I was saying earlier. This rate right here is really no longer the rate that we control. We cannot tell people that people of utopia, you can only grow, this population can only grow by 4.5% in 2001. No, we cannot tell people to follow that rule. Okay? As a matter of fact, again, as I said, this is only something that we observed. So a year later from 2000, a year later, exactly 1 year later from 2000, we notice it has increased by 4.5%. And we further observe for 1 more year. In 2002, another year from 2001, we further observe that, hey, it's still going with that rate right there. And then the scientists stay there for 1 more year. So 2003, another 1 year after 2002, the scientists measure the population there again, count the population there again, and notice it was another 4.5 from the previous year, 4.5% growth from the previous year. And so this is now enforcing the understanding that this growth right here, yes, it's a yearly growth. It's a yearly growth rate. It's a growth rate per period of time. But it's only an observed one. It came out simply because we observed it. It simply came out because we observed it. Okay? So that means now let's make the connection. When we were doing money math, when we were doing financial math, when we were still able to control the growth ourselves. See, this nominal rate right here is kind of indicated that it's the kind of rate that we can control. And when we let the plan become the continuously, when we let the plan to be, compounding interest continuously, then the plan produces the effective rate right here to be something higher than the nominal rate. And this effective rate, in the way how I explained it, it came out entirely as what we observed. We observed how our money grow following this continuous plan right here. Following this continuous plan. Growing. Observed rate. Observed rate came out to be effective rate. Observed rate came out to be effective rate. Observed rate came out to be effective rate. All right, so just now I made that connection. Observed rate from in the money math, observed rate was understood as effective rate. And so now, really back into this problem, and I made my arguments now. This 4.5 is not the rate where we decided it. Nope, it's not the rate we decided. It's only the rate that we observed. It's only the rate that we observe. That means it's already been continuously growing. The population has always been continuously growing. All we can do is we observe, and we found out, we discover that in every default time period, in here it's a year for each period. So in every year here we notice there's a 4.5% increase. Okay, 4.5% increase right there of that population. All right, so now clearly making that connection, if this population was the money, if this population was really the money amount, then, ladies and gentlemen, 4.5% is clearly not the nominal rate, is not nominal rate. And I'm still using some financial math term right here, even though it's not really applicable to the world of natural processes anymore. But allow me, because we've spent so much time in there, and I want to make some, some transformation between the concepts we've learned in the financial math, and we bring it outside to the outside world right there. Okay. So clearly 4.5 is not nominal rates. Nope, it's not. All right. But 4.5 here is, I argued that earlier, it's the observed rate, and so in that way, right here, it's if the concept of effective rate exists in natural processes, then this is truly effective rates. Think about that analogously like that. Okay, so this what I rate right here is not the analogous nominal rates. It is analogously the effective rate. It's similar. So when I'm saying it is the effective rate, I meant it's similar to the effective rate right here when we were growing our money continuously. Because this is only the rate. The only thing we can say is that we have observed that there's been a growth of 4.5% yearly. All right. So that's the connection. So, but when I'm saying this rate written right here, this rate written in the problem is not the nominal rate, I didn't mean that the nominal rate doesn't really does not exist any longer in the world of natural processes. Nope, it's not really that. It still exists, but we use that in a different way. We will use that in a different way. We will use that concept analogous to nominal rate in a different way. Okay, we will use that concept analogous to nominal rates in a different way. So right now, all I'm introducing is this rate is something that's similar or analogous to effective rate only. It's entirely and definitely not anything similar, not even anything similar to the nominal rate at all. Okay, so now we can take that out. So now I can say that this is similar, okay? Similar to effective rate. All right, this is something similar to effective rate. But then we don't really call that effective rate anymore in the world of natural processes. When we stepped outside of financial math, then we leave the term effective rates back in the world of financial math. We can't really carry this term out. So sooner or later, I'm going to come to the showing what exactly is the term for this. Okay, but for now, allow me to move on a little bit. All I'm saying now is this 4.5 is similar to the effective rate. That's all we know. Okay, and so now in that understanding, this is one thing we can do. You have seen this already. I've done this work earlier, even before we got into the financial math. So yes, the function that models this population, the way how we work is still the same. So think about in T years. There were 25 million in the beginning, because year 2000 was T equals 0, the initial time. And so in some T years later, it's 1 plus 0.045 to the T. Because even if this really was the money math, and once we have recognized that this is the effective rate, and it's 1 plus effective rates raised to the T power, and then multiply with the initial amount. And then this is not anything surprises us at all. Not anything that surprises us at all. We have seen this even in my initial explanation, in my earlier explanation when we were briefly looking over these. But see, behind the scene in my mind, in my thought process, I was seeing this entirely as an effective rate the whole time when I was explaining it. But my explanation at that time I did not even bother getting into any of the distinguishment between effective rate and the nominal rate and all that. So we think of that here. So the way how I derived was still the same, and it's still gonna be the function, okay? But we gotta realize that this is just not the nominal rate. It's not even anything similar to the nominal rate. This is just at the most. We can see that this, as a connection with the money growing, and this is similar or analogous to the effective rate. And so yes, this is 25 millions as our final expression of the function times 1.045 to the t. So now we're working with this particular problem one. We have already come to this function, this exponential function as a base 1.045t. And our model is entirely continuous. Our process here is entirely continuous. All right. Our model is entirely continuous. I keep emphasizing that. So now in that way, now I can put away all of this. So our population growth right here is entirely a continuous growth. Okay, it's entirely continuous. That consequently, or as an impact right here, we can re-express our function here. Q of t can be re-expressed. As some function with initial amount, but in base e, we can re-express that exact same function. Because this function, if it was a money problem, I'm explaining that this function only gives us a sense about how we can observe the change in the population, once in every default period of time. So here in this problem, the default time period here is every year. So with this function, it's faster for us, and it's good for anyone who doesn't have a base e on their calculator to quickly observe and quickly predict that, how large the population will be in 3 years, in 10 years from 2000, in 21 years from 2000. Okay, but the process itself, the process on its own is already a continuous growth. And you can also use this model to find out, to predict how high the population is in 3.5 years, in some decimal number of years after 2000, because the process here is already a continuous process. And so in that way, now knowing that this is just one expression, but the process itself is a continuous process, then we can alternatively, but I'm saying alternatively, making it seem like it's not important, but it is important. We can re-express that same function q of t that models our population as a base e exponential function, base e raised to some kt. All right. We can definitely re-express this function that models our utopian, the population of utopia in a base e as an exponential function, but in base e right here. And so now if we're looking a little more closely, then see, so now again, just going as closely as possible as we move on right here. Try to move as closely as possible and as side by side as possible with the money problem right there. Think of the population as the money amount in your investment bank right here. Then once we're investing with a continuously compounding the plan right there, with a continuous compounding plan, then this k right here was indeed equivalent to the nominal rate. This k right here, if our population here was a money growth with some nominal growth rate, then this k in our exponential function base e here is the, again as a reminder, this is equivalent to the nominal rate or analogous to the nominal rate. That's how I see it. And so now we have that important, we can bring out that important understanding again. So still at this point, all I can see is 4.5, right, percent is similar, or is as of now we can think of this 4.5% is thought of as or can be thought of as effective rate in a money math, in a financial math. And then this k in our exponential function that models this continuous growth process right here, this k can be thought of as the nominal rates. That's the difference right there. So definitely 4.5% is not k. Definitely 4.5% is not k. 4.5%. If this population was a money population, was a money quantity, then 4.5 is the effective rate. Whereas this k is analogous, or this k at this moment can be thought of, okay, as the nominal rate. Okay. Somehow I skipped the word rate right here. All right, k can be thought of as the nominal rate. So now once I brought in that understanding, then we can see the following connection. Because in the end, what's the goal right now? What's the goal that I'm trying to lead you into right now? I'm trying to lead you into finding the other form, finding how we can re-express q of t in an exponential function with base e. So really the only struggle we face is how to find that k. We already know the value for base e, and indeed we already knew the initial amount being 25 million. The only challenge for us right now. We may struggle a little bit, but we will overcome with that. Find out what that k value is. And for now, as I said again, I'm writing the term nominal rate here because if this was money problem, then yes, that k was the nominal rate. And then so as of right now, as we're thinking of this population, then k can be thought of as the nominal rate. But I keep saying it's not exactly because we no longer doing money math anymore. Okay, and then I will eventually mention all of those terms like that. Okay, so right now, yes, we can think of k as the nominal rate. And so now we already knew this important relationship. 1 plus effective rate equals e to the k. 1 plus effective rate equals e to the k. This k is thought of as can be thought of as the nominal rate, whereas this 4.5 is thought of as the effective rate. And so in that case, as a consequence, I can see that in my next step right here, it's 1 plus 0.045, because this 0.045 is can be thought of as the effective rate. And so 1 plus 0.045 can be equated with e to the k. Or in another way of saying, it means 1.045 equals e to the k. 1.045 equals e to the k. Okay, and so now in that way, ladies and gentlemen, this is the whole reason why in the end, the whole lengthy lecture here, yes, admittedly it's quite lengthy at this point, but the whole idea here is about how we see different applications of exponential function. clearly it has always been about exponential functions since the beginning. But somewhere here and there, as I said much earlier, somewhere here and there we keep seeing logarithm coming in as an application. This is where I'm seeing it, because now what we have here is an equation in exponential form. And so now I'm going to re-express this exact equation in logarithmic form, base e. And so that means here, rewriting this equation in logarithmic form, I'm now looking at k value. And remember, right now our k can be, we are thinking of k as the nominal rate, analogous to that nominal rate in money problem right there. Okay? And so now k, if we think of k as a nominal rate, and nominal rate equals natural log of 1.045. That's how it is. K equals natural log of 1.045. Okay? Feel free to pause the video if you need to and take note on this work right here of mine, and particularly this argument. And feel free to rewind if you have to hear my explanation again. Okay? But now I'm about to swing over to the calculator to quickly do a calculation here. Okay, and then I'm going to come back, and at this point we are as a big impact right here. We have found our k value right here. For now we're thinking of that as a nominal rate right here, but we have found that that value for k right there, and we are ready to finally come up with our function, our modeling function in base e right here, in base e. Okay, all right. So now, on my calculator, with the standard TI calculator, all I'm doing now is natural log, because we are calculating the value for k. So natural log of 1.045. That is now 0.04401688854, and the calculator is only showing this many digits, but there are going to be a lot more after that. So I'm just going to round to 5 decimal places. Okay, so 0.04402 right here. That's all I need right now. All right, so 0.04402. That's my value for k right here. So now I definitely need to erase a lot of these explanations I've had on the board right there, assuming you have already copied it down. All right, so now our function q of t, the same function q of t, but now it can be written in base e as following: 25 millions. Okay, times e to the 0.044, okay, 0.04402 t. All right, 0.04402 t. Yeah. That's how I'm seeing it. So now you can see that. See, so with this nominal rate, once again, think as closely as we can to the time we were doing money math, and think as side by side as possible with money math right here. So if this is some initial amount of money, and then our money has grown according to some continuous compounding plan like that, then this is equivalent to a nominal rate. So isn't it true that nominal rate will always appear to be slightly or maybe greatly lower than the observed rates, the effective rates? So if this was a nominal rate, and observe how it is, it's quite below the 4.5 right here. So what we observed here is 4.5, and that's convinces us even further that this rate here, as an observed rate, okay, is the effective rate right there, analogously to or similarly to at least similarly to the effective rate when we were doing the financial math problem like that. So 4.5 is surely higher than 0.04402, because 0.04402 is only about 4.402%. This is 4.5%. I mean, when we're talking about growing by millions a year, then it makes quite a difference between the two rates. But then the other nominal rate was when it's growing continuously with base e. And that's why, so now ultimately speaking, this is just another expression. Okay? Or in other words, this function and the other function, 25 million times e to the 0.04402 t will give the exact same prediction in t years as if we were using this model right here. So these two functions are exactly the same, exactly the equal, the two equal functions. Yeah, the two functions. It's just they re-expressed in different bases. Okay, so now after that way, after those explanation right here, so now let's give some formal term right here. Let's give some formal term. Okay. So now we know that this form right here is an alternative form. But now when we write, so the model, when we're stepping outside, again, when we're stepping outside of financial math problems, then any of our natural process is already a continuous process. The process itself must be a continuous process. Okay? But then the way how we write our function, this is regarded to as this function in this form with base e. Among the scientists and the mathematicians right here, we call this model the continuous model. So when you're writing, so the process is always continuous, but the way how we write the function, the form of how we write the function when it involves, when we stick with base e, we call this form right here. Well, when we stick with base e and we see this form, we call that this is a continuous growth. And I should have used red ink right here. Okay, this form right here is called a continuous growth. It's just a name right there because we see base e. The process itself, as I said again, doesn't matter if we use whatever of the two forms. The process itself is always continuous. It's always growing continuously. But then, particularly now, when you hear the term write the continuous growth model, that's the one right here in base e. Okay, write the continuous growth model. Then this is, we have to write that in base e right there. Write the continuous growth model, the continuous growth model to predict the population in some t years. This is the model right here because we stay with base e. And so if this form right here, if this form of the equation using base e is called continuous growth, this particular value right here, this value for k, this k right here, we don't call that nominal rate because again, remember, this is not money math any longer. We already stepped outside of the world of financial math. And so now the value for k in this problem, okay, is called, k is regarded as, k in this case here is called, now quite commonly people refer to that as a continuous growth rates, or just for short, continuous rates, okay, continuous rate. Professor James Stewart, who writes a lot of math textbooks out there, that one of my favorite professors, I mean, not directly my professor, but one of the professors that I really enjoy reading his math textbooks, a lot of his math textbooks. Sadly, he passed away a few years back already. But Professor James Stewart, throughout all of his textbooks, he referred to this continuous growth rate here as relative. So you can also, somewhere here and there in some textbook, and especially throughout all of the textbooks from Professor James Stewart, he will refer to this term right here as the relative growth rate. All right. So relative growth rate or continuous growth rate is the kind of rate that's similar or analogous to the nominal rate in financial math problem. And we use that. We use continuous growth rate when we write our function in continuous growth form. When we write our function in continuous growth model over here. So maybe a little more precisely, this is continuous growth model. Okay, because we use base E. All right. And then this is the part where it's starting to get a little tricky right here. So it's just, so at this point, I'm sure anyone viewing this lesson is clear which one is which. What matters is how how you can understand the wording that's communicating to you. The way how the wording is communicated with you, right there. So right now, when you see the equation, the term for that is continuous growth rate or relative growth rate, according to Professor James Stewart. Okay. So that's clear. Anytime we hear that term, that terminology, we use this form. Okay? But then, for this form right here, okay? Now allow me to erase all of these extra explanation now because we're all clear. So this form, we're just going to call that some textbook refer to this to be a little more precisely, yes, periodic growth model versus continuous growth model. But that can also worry some people, particularly me when it was my time learning about this. That also, this word periodic also worried me in some way because it made me at first sight think that this was only the sort of like the screech, like the population only jumped in every 4.5 in every year by a 4.5. But so it's used the term periodic here simply just means the rate here is observed. The rate here is an observed periodic rate here. Okay, the growth rate here is the observed periodic rate. But in the end, the process, that's why I keep yelling it out loud, the process itself is always continuous process. Okay, so periodic growth model over here is just simply the way how we write our function using the observed periodic rate. So I actually use the term observed periodic rate, periodic growth rate. But as a matter of fact, most of the professors out there, most of the textbooks out there as well, just simply stick with the term growth rate. Okay. So when you just hear growth rate without indicating continuous, without indicating the being relative, then it's just periodic. So automatically, without the term, without the extra description being continuous growth rate or being a relative growth rate, then it is automatically understood as the periodic growth rate right there. Okay, so periodic. If we see the term periodic here, it's even better. But otherwise, it's just fine. We don't see that. It's just a growth rate, but it's automatically understood as the periodic growth rate right there. Okay, and that is already something that's analogous, something that's equivalent to the effective rate if it was money math. All right, and so in that way, so now let me swing back to the wording of the problem because right now we're working through problem number 1 right here. Okay. So now looking at the wording of the problem, this is the original wording right here that I brought it up in problem 1. So now let's say if you're in a situation where you're reading the description of a problem and you are asked to come up with a model with a function that models the population growth according to this description right here, then just simply by reading this rate right here, how do we know if it's periodic rate or continuous rate? See, without any indication, without any special indication that it's being relative or being continuous, then this rate right here given, and it has a term per year. And it has a term per year right here. So that's automatically making it, this is periodic. And so now, after recognizing that this rate right here, even though the process must be a continuous process already, but this rate right here is in the way how it's indicated it's indicating a periodic growth rate, or just simply for short, just some general growth rate. Then in a problem like this, if you are asked to write the modeling function, usually it comes to this version right here. But you can still spend extra step to come to the other version in base E, but this is the default version that comes when the wording of the problem describes simply just some general growth rate per year, some growth rate per period. That's the idea. Okay? And now back on the wording of the problem. So just like that, exactly the same problem, but see, some other textbook author can write it in the following way of wording it. See, the population of Utopia was 25 million in 2000 and has been growing, see, continuously by approximately 4.401 per year. 4.401 per year. Admittedly, I have a little typo here, but on the board earlier it was a 4.402% per year. But so now, see, this value right here is consistent with our calculation earlier. This is see, e to the 0.04402 right here. And again, as I said, I had a little typo on my computer screen earlier, but so that's how it came up with. So sometimes the wording of the problem can be directly giving you a continuous rate, like the one we just saw in here. So the same problem there, but it could be the same problem, but it could have also been written as, you know, the population was growing continuously by approximately 4.401% each year. So this is now, when you see that term continuously, it will clearly catch your attention that when we're writing this, the default version of the modeling function has to be in base E. So when we're seeing that right here, then it's easier to start out with base E first. And then right there, that's our continuous growth rate is to be used there with the initial amount right there. And then if you want to, if you would like to, or if you are asked to write the growth in periodic growth right there, then you can re-express this. Okay? But so just like that, see, in the way how a lot of problems in Professor James Stewart's textbook were written, and then instead of writing growing continuously by approximately 4.402% each year, Professor James Stewart, in a lot of his textbook, he wrote growing at a relative rate, at a relative rate of about 4.402% each year. And once again, forgive my typo error right here. Okay. And so that's how, you know, one same description right there, but can be written in two different ways depending on how we recognized about the rate. Right there. Okay. And so now, again, at this point right here, the rate, when we are now stepping directly into once we know that we're only working with those natural processes outside of the money problem right there, then now at this point it only matters between, is it a periodic rate, periodic observed rate to be precise, something that's analogous to the effective rates for money math, okay, and then, or it's the relative rate or continuous rate analogous to the nominal rate. And so in that way, we don't have to write R sub E anymore, because R sub E is the symbol used among the financial experts right here, indicating effective rate. But now we can just that same equation, effective rate plus 1 equals e to the k, e to the nominal rate. That same equation, now when we're working with natural processes, that equation becomes 1 plus r equal e to the k. So it's still that exact same equation, but it's just now r is the periodic rate. Okay? And then k is the continuous, okay, rate. That's what it is. And so that's how it is. But a lot of times, some textbook, skipped out that explanation, that bridge over between the money math and here that making it seem like too easy that any starting rate is that. But really, this is, yes, it's a periodic rate, but you have to always keep in the back of your mind the process itself. Okay, the process itself is already a continuous process. So you don't have to do any compounding of the growth on that rate any longer, and that's how it can be easily equal like that. All right. So what about an exponential decay process? So I started out with this population growth here. So it was the problem we just did here. The problem we just did here was an exponential growth because the population itself was growing. And in my definition earlier, it was growing and according to a modeling function being an exponential function. So yes, we can call this problem just now an exponential growth problem. Okay, that was problem 1. Okay, so now, as I mentioned just now, so what about in an exponential decay problem? I mean, so in business math, a lot of time we're looking for money growing, so we don't see much exponential decay problem in business math, in financial math. But now for natural processes out there are processes where a quantity is losing on its own, is losing itself naturally and automatically over time like that. Okay, and so in that way, now let me bring up that problem we have done already, and then let's bring it out again, and then give a completely in-depth look at that. Okay. All right, here we are at problem 4 that we have brought up earlier. Now let's, as I said, let's give it a closer look and a much more in-depth look at what we were doing. So clearly I made my arguments earlier, way earlier, that this problem is an exponential decay problem. Okay, so now I'm going to extract out some information on the board right here. Okay. And then at this point, as soon as I write down and sketch down the information, then we can start applying it's not a formal example, it's only a demonstration problem, but we can already apply our understanding what we have constructed throughout by the end of problem 1 that I just introduced about the population growth. So now there's a growth or there's a decay, there's a population that's getting bigger or there's a population that's losing its own right here. So the population we're looking at here is a quantity of bismuth 210. Okay, and so now we have an initial amount. We have an initial amount being 10 milligrams. Started out. Okay, and then the rate here is indicating, so the wording, again, let me bring it on the computer screen right here. The wording is saying 10 milligrams of bismuth 210 isotope reduces about 13% each day. 10 milligrams. So that's the initial amount, and then it reduces. So this is the rate right here. 13. It's losing itself about 13% each day. Okay. And so in that way, I'm seeing the rate here is. The wording says reduces, or it's not the rate reduces, of course it reduces, but the rate here is how fast it's reducing, 13% each day. Okay, all right, and so now along with what we have already learned, and see this term here, this wording here, and the entire problem did not come with the word continuous. So the rate here is not indicated as a continuous rate. And as a matter of fact, it's indicated in, it's that percentage each day. Okay, a couple things to find to also point out right here. Each day, so we have a time here. T variable is time is in days right here. Okay, and then this each day right here is the default time period. Okay, so in a few days later, it's gonna in 1 day later it already loses 13% of itself right there, and in the next day another 13%. But I made my arguments earlier, and here is that same logic again. This process on its own is in no way a discrete process at all. Okay, this process, in other words, must be a continuous process already, even though the rate here is not clearly indicated that it's a continuous rate, but it's okay. Right now it's written as a periodic growth rate right here, or just some general growth rate per default period of time. Okay, it's not so the word continuous rate is skipped, compared how we have seen that in problem 1 earlier. Okay, and so, but now once again, keep in the back of your mind, this is already a continuous process. It's a continuous the decaying process. It's losing itself every day like that. So this rate right here is a rate indicating the rate for losing itself. So that means starting out with so we have come to the following. And by the way, I'm letting Q of t to be the amount in t days. Okay. All right, the amount in t days. And so for that reason, the amount is the function Q right here. So we can call this 10 milligrams right here as Q sub 0. All right, and so this is what we have seen earlier. So now, when I was working on this problem number 4, way at the earlier time of this lecture right here that I'm talking about, I finalized this function, this exponential function as so 10 milligrams times 1 minus 0.13 to the t. And so it's minus, and we had a formal definition, or more like a formal agreement that any time, so with whatever given rates, but anytime it's a rate indicating losing of the material, losing of the quantity, or losing of the population, then we're going to have to go 1 minus the rates to the t. So we're just exactly following that. And that's what we did, okay, earlier, because here I'm not really going to repeat the whole problem like that. And so 1 minus 0.13 is concluded, or is finalized, is simplified down as 10 times 0.87 to the t. It's an exponential function, ladies and gentlemen. And so now, alongside with what I have just explained about the concept of continuous process, but we have periodic rate indicated instead of continuous rate. So here it's periodic rate indicated here. So this model Q of t equals 10 times 0.87 t right here. This model is indeed, so it's more direct. Anytime our problem has given us a rate that's just generically written like this, not specifically as a continuous rate, or not specifically as a relative rate, rather than just a general rate like this, then the more direct version is this one right here, where it's in terms of the base, where it's 1 minus the given rate. But again, keep in mind, yes, we call this the periodic. Yes, we call this model periodic growth model, okay? But the process itself, so model is just a function, and then periodic here, to clarify, it's just the idea of, it's just to indicate the fact that the rate is written is indicated as a periodic rate, but it's completely observed rate. Okay, nothing under our control anymore. We cannot control, how this substance is losing on its own. We cannot control how this chemical element is losing on its own. We cannot make it go slower. We cannot make it go faster. It just go that way, the way it is by nature. And all we do is we observing it. Just like how I was saying earlier, we cannot control how the population in utopia is growing. We cannot make it grow faster. We cannot make it grow slower. Okay, we only observe. And that's why any of these is equivalent to the effective rate when we were still doing money math like that. Okay, but now it's a decay problem, so that's why I have to explain that after explaining about a natural growth process. So now we just know that this is periodic growth rate, but the process is always continuous. Okay, so the function here is called a periodic growth model simply because the rate used in here is a periodic rate written right in the problem like that. Because this rate here, didn't come with the word continuous or didn't come with the word relative. Okay, so now once we finish writing one formula here, which is a lot more direct because it comes straight out from this periodic rate right here, we're in that situation where, hey, what if we desire to re-express? What if we want to re-express the same Q of t right here as a function in terms of base e? All right. So now I'm just putting that in a way that we want to write that in terms of base e. Okay, so now let's see how. So just like that same argument I've made in that similar argument I've made in when we were going over problem 1 just earlier, then Q of t, our quantity growth or our quantity decay right now, our quantity that's losing itself, can be expressed, okay, in the form Q of t equals Q sub 0 times base e raised to the power of kt. Okay, in the form of power of kt right here. And as a matter of fact, so now I'm going to have to make it even more clear right here. It's a process where it's losing itself. Okay, it's a process that it's losing itself. And so eventually I'm expecting that this k is negative. Okay, eventually I'm expecting that this k has to be negative. We will get to that. Okay, we will get to that. All right, so but just right now for a scratch, I just want to bring it in right into that general form. So we want to express Q of t can be expressed. I should have said re-expressed. Okay, Q of t can be re-expressed in the form of base e. This is the initial amount. So yes, definitely it will be 10 milligrams times e to the kt. And all we have to do now is find out what that k is suitable for this function. What is the k value that's suitable for this function? And yes, this k here as a reminder now from what we have just learned previously, then this k is regarded as this k right here. Now we call that it's the continuous rate. We're no longer working with financial math. So let's call that with the formal term now for all the scientists to use. The formal terms that the scientists outside of the aside from the financial math experts, then the scientists call this the continuous rate or relative rate. Okay. So now, in that way, here's how I'm seeing it. That relationship I pointed out at the end of our work, our in-depth work just now over problem 1, we can use that again, and we will be staying with that quite often. 1 plus the periodic rate. Now I don't need to write the subscript e. 1 plus the periodic rate equals e to the k. 1 plus the periodic rate equals e to the k. But then it's not quite, so when it was growing, then when it was growing, and yes, it was 1 plus the rate. The rate is just the rate. But now if we observe this form of how I came to that 0.87, then in a way we already understood, then this process itself is losing its own population. This material is losing its own. And that's why we subtract the rate instead of adding. It's a decay process. It's a natural decay process. It's an exponential decay process. Okay? And so in that way, yes, theoretically it's 1 plus r, but the r here is a negative. So now the better version to write now is going to be, or how about I should have said 1 plus r equals e to the k. This was for growth. Okay? Now for decay, because we clearly realize that this problem is the decay problem. This same equation becomes 1 minus r, because this is how we constructed our periodic base right here. 1 minus r equals k. That's for decay problem right there. So this is where we're now quite far away from the financial math. But see, we took the idea to build this, and then from that we led on to this. That's the idea. Okay, and so now 1 minus r will be e to the k. And so now we are quite ready. So that means it leads to 1 minus 0.13. Okay, and we want that to equals e to the k. We want that to be e to the k. And so that leads further to 0.87 equals e to the k. 0.87 equals e to the k. Okay, 0.87 equals e to the k. And so now I keep repeating that for a few times already because I want to emphasize again. In the end, we keep looking for applications of logarithms somewhere here and there, because the whole time I'm going over here with anyone viewing this lecture is all about first pointing out the existence of exponential functions. And then here I'm on my way to eventually, we will be at some point where you should be able to derive your own exponential function that models your problem. So this is all about, as a primary goal over here, applications of exponential functions. But anywhere here and there will be logarithm operations become handy in our problem. So anywhere, in any step we're moving here, there will be applications of, or scatterly, there will be applications of logarithms. So the reason I said that, right here, 0.87 equals e to the k. This is an exponential form of our equation, or our equation is in exponential form. So now I can easily rewrite this same equation but in logarithmic form. This is base e, so now I'm writing that as natural log of 0.87 to equal k. And now all of a sudden we realize, wait a minute, we have found a value for k. K equals, precisely speaking, natural log of 0.87, which is a finite value. It's not going to be a nice looking number, I admit, but it is a finite value. All right, so let's find out what that is. And for anyone viewing the lesson here, go ahead and copy the notes here, because as soon as I come back from the computer screen, which I will show, I will erase this to put all of the information here into that form of our modeling function. Okay. All right, so now with our calculator. So natural log of 0.87. All right, so now we come out with the negative 0.13926. Okay, negative 0.13926. All right, so now I've come to a value, okay, and allow me to write that in 5 decimal places. So now my k value So I've now come to finish calculating my k value to be negative. And as I was saying earlier, see, this is a decaying process, so k will eventually be negative. And this is how it turns out, like that, consistent with what I said earlier. Negative 0.13926, which is nearly 14%, nearly 14%. Okay, but I only round down to 5 decimals here. So now this is going to be our continuous model over here. In base E, we can re-express our function, our modeling function as Q of t equals, so the initial amount is here, 10 milligrams at start, Okay, but at some t years, at some t days later, it's going to be 10 times e to the minus 0.13926 t. That is how I have completed my what's so-called, with this model right here. Yes, now I call this the continuous, continuous growth model. All right, continuous growth model. All right, and then yes, continuous rate now equal. So now I can just highlight this right here. I can highlight this right here. Yes, that is our continuous rate. Okay, or we can call it as well as relative rates. That's what it is. All right, and so now, and of course this problem, once we have had some understanding prior to it, okay, then at a point prior to this, getting into this problem, then it has gone a lot faster than how I went over problem 1 earlier. So now on the wording of the problem, okay, with the wording of the problem, so the same wording of the problem right here, it's only indicating just the periodic growth rate right here. And that's why a little more directly, it's convenient to write immediately from that form, from that worded instruction into the periodic growth model right there. Even though the process itself, again, already a continuous process, but we can conveniently write down immediately the periodic growth model. Okay, using this this growth rate indicated without the term continuous indicated with that. Okay, and then the same wording, the same problem, really the same problem, the same process right there. But now we can word some other times the same problem, but it can be worded as 10 milligrams of bismuth 210 isotope reduces continuously at about 13 points. See, so now so in some other time, that's what I'm saying. In some other cases, the exact same problem, but it can be given to you with the term continuously. Okay, continuously about continuously, and then about 13.926% each day right here. Or according to Professor James Stewart, that in a lot of his textbook, if he was asking for it as a continuous rate, then he would use a term at a relative rate of about 13.926 each. So that's just two different ways of how the same problem is being indicated. Either we are indicated by just some general periodic rates like this, or using specifically the continuous rate. So continuous rate will a lot of times looks a little bit different from the periodic rates. And then continuous rate is the same as relative rate. Yeah. All right. And so that is the two functions right there. Okay, so I did not do this with problem 1, but now with this problem 2, let me show, and it should have been the exact same with problem 1 as well. But now let me quickly show the graphs after I erase the board. I just want to clear some space. So continuous growth model is here for the exact same information. And then before getting into this, before coming up with this, we already had Q of t equals 10 milligrams, same initial amount, and then times 0.87 to the t. The exact same function. These two are exactly equal. Okay? But written in different ways right there. And so I already named this. This is the periodic growth model. Okay, periodic growth model. And so in that case right there, allow me to show the graphs. Okay, and I purposely showed both. I want to show both graphs, so allow me to also show how I put in the function as well with decimals here. Okay. And so now, first I'm gonna type. How about for the periodic one? I'm gonna go with p of t. Just it's for the same population, but I have to name the function differently because one of them is the periodic version, the model, and the other one is the continuous model. So p of t is for periodic equals 10 times point, and right now at this point, let me hide away the graph like that. Right, 10 times 0.87 raised to the t. All right, so this will be our function. All right, so now from the left to the right, yes, it makes perfect sense that, and the initial point is on this axis right here. The initial point is 0. So the axis here is the t-axis. So when it's time 0, see, that's why we're starting out with 10 milligrams at start, and then we keep losing. So the height of the graph right here is the amount left over. All right, so as an exponential function, this graph keeps losing itself right here exponentially. All right, and then see, in some far long run right here, the graphing utility itself may fail to show the difference, but if we keep zooming in, the graph is still going to be above, and now you can start seeing some difference right there. The graph will be still above the x-axis. So the graph of any exponential function, as we have already learned, will never cross through the x-axis. It's only asymptotic. All right, so that's our function. And now I'm going to hide this graph. I'm going to type in the continuous model, c of t. Okay, and that's 10 again. And allow me to, and before I complete this, allow me to hide that graph away. So now it's e to the negative 0.13926 t. All right, so now with this graph, I'll show that in blue color. All right, so the graph in blue is here. It's a decay process. No wonder why and that's the reason why it's falling down from the left to the right. And then now I'm putting together with the red graph that we've had earlier. And really, I cannot see the difference anymore. The red graph is here, and now the blue graph is here. Okay, they are just exactly the same. And now let me even adjust the setting of my screen right here so that we can see the graph even better. All right. Or I may even hide away all the grids. Okay, so again, the graph in blue is here, and the graph in red is here. It's just about a matter of about blinking away the color, but it's really just the same. The two graphs are identically the same, even though the functions are written differently. But the two graphs coincide like that. It's indicating the fact that these are just two different forms, two different expressions of the same model function right there, of the equal model function. All right, so now we have learned how we have derived our continuous model function for either a growth or a decay. I need to make some corrections here because it's just now realized that this cannot be called growth, but it needs to be considered as continuous decay model, because the problem in this problem we are losing the quantity, so this is decay problem instead of growth as earlier. Okay, and then yes, the rates. So k here. So this k we found being negative. See, it's a decay rate right here. So no longer a growth rate, but it's decay rate, negative 0.13926. Okay, and then so we call this is continuous decay rate, or it's growth, but it's growing in a negative way. That's another way of seeing it. Okay, or relative decay rate, and then this is just so what we have there is so R equals 0.13 is the decay rate. All right, and so So in my earlier part, if I might have in earlier part where I worked over this problem number 4 here, I might have used some terms where I mistakenly use a growth model or a growth rate. This problem, you just turn the word from growth to a decay, like that. Okay, and that's how it works. All right.